आज रवि
Yes.
सर आएंगे?
हाँ 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 सर, ज्वाइन कर चुके
अच्छा
हैं, मीटिंग में है जी।
अच्छा, ठीक।
So I welcome our esteemed speaker, Dr. Ravi Kumar sir, Ravi Kumar Sharma sir. Good evening, sir.
Good evening, Dr. Abhishek.
I am very
How are
much
you?
thankful. Fine, sir. I am very much thankful to you, sir, for accepting the invitation to deliver the talk.
Thank you very much for
It is
inviting
my
me.
proud privilege and pleasure to introduce our today's speaker, Dr. Ravi Kumar Sharma, sir. Dr. Ravi Kumar Sharma is currently working as Directorate of International Collaboration, Manipal University, Jaipur, and also as a professor in the Department of Mechanical Engineering, School of Automobile, Mechanical and Mechatronics Engineering. He has served this institute as Directorate of Internship Cell during August 2020 to May 2023, and currently heading the Department of Mechanical Engineering. He earned his PhD in thermal engineering from the University of Malaya, Malaysia, and has worked in various reputed Indian and foreign universities. He has published more than 80 research articles in International Journal of High Repute with high impact factors and presented his research work in many international conferences in India and abroad. He has also written 7 book chapters and edited 4 books and reviewer of many international journals. He has also delivered numerous invited and keynote speeches in faculty development programs, short-term training programs, workshops, and conferences. His current area of research is renewable energy and thermal energy storage, in particularly solar energy. His primary research is focused on the development of phase change materials or rapid heat transfer by enhancing thermal conductivity. Dr. Sharma has supervised 5 PhD successfully and currently supervising 3 PhDs. He is also working on the development of waste carbonized materials for energy storage purpose, fulfilling the sustainable development goals and circular economy. He has been also listed among top 2% scientists across the world as per the list released by the Stanford University in the field of energy. So I again welcome you, sir. Over to you, sir.
Thank you, Dr. Abhishek. And thanks to all the organizers for having me, for giving me an opportunity to speak on what we do in our laboratory along with my research group and collaborators. And thanks to all the participants who are here. Even this is weekend, but I can see a lot of number here. What I can see is 166 people have already joined. Now 169. So it's good to have this big number. So anyway, I'm not representing Directorate of International Collaboration here. So I'll be discussing more on what research we have done on thermal energy storage materials. What are those materials, and how can we modify to make the optimum and the maximum utilization of these materials? So,
Sorry
Doctor,
to
can
yes,
yeah,
sorry,
please, please,
sorry to interrupt you, sir. I am
please.
very happy to share that, sir, we have 479 participants, and very
Wonderful.
soon, sir, you will see the figure about 350. And participants are from 23 states of our great nation, sir.
Wonderful, wonderful.
Yes, sir.
So I have never spoken in front of so many people.
Yes,
So
sir.
it's a
Thank you.
great moment for me to speak and to interact with so many people on the single platform. Thank you very much for
Yes,
having me here.
yes.
So can
Thank you.
I share my screen now?
Yes, sir. Yes, sir.
Okay.
Mulli, have
I
you
hope
made over?
Yes, sir. Yes, sir. Sir.
Okay, thank you.
yes. I hope I'm clearly audible and visible.
Yes, sir. Audible and visible, sir.
Yes, sir.
All right. Right. So is it visible?
Uh, right now, yes, sir.
Okay. So let me change the slide and let me know if you can see.
Yes, sir.
All
Slide
right.
is also changing and visible, sir.
Perfectly, perfectly. So I'll roughly take 1 hour to 1 hour 5 or 10 minutes, and I'll try to stick with the timing. Though there is a lot to speak on thermal energy storage and the materials for thermal energy storage, but we cannot speak on everything. So I'll try to stick with the timelines. So this particular presentation has been structured into these few things, as you can see on the screen. I'll be I'll briefly introducing this area, and I'll tell what storage of energy is, why is it important, and then the PCM options. PCM stands for phase change materials. I'll tell what these are and what these means and how do we use them. And then thermal cycle testing of these materials, then the composite PCMs, and then the applications of these materials. So a little brief of my workplace where I come from. I am currently working with Manipal University Jaipur as professor and head of mechanical engineering department. This university established in 2011 in the outskirts of Jaipur. Currently has more than 16,000 students on campus and more than 700 faculty members plus uh, 300 non-teaching staff and other people. So this university has seen a tremendous growth over the period of last 1 decade. But basically, we this university belongs to a family which has an educational background of more than 70 years. So we are a part of main Manipal group, which is in the Udupi district of South Karnataka, near the coastal area. Currently, Manipal Group has many universities, three universities in India, and one university in Malaysia, one is in Dubai, one is in Nepal, and the one is in Antigua. It's an American University of Antigua. And the Manipal Group is famous for medical and other educational institutions. So we do not have medical in this campus, but we do have science, engineering, and other aligned streams. So coming back on, yeah, we do have many research infrastructures available in the university. So I'll not be speaking on them. So now let's come back on uh, what thermal energy storage is and what thermal energy storage materials are. So in order to understand these thermal energy storage part, let me introduce you, or let me take you through a small journey, starting with the environment. The environment we live in, what do we call environment is? So environment is everything that surrounds us. It may be land, it may be air, water, natural resources, flora and fauna. So everything that surrounds us becomes an environment, including us. And to protect the environment, there is a lot of things which have been doing by the world leaders, scientists, and the researchers. Everybody is after the environment now. Everybody is deeply concerning about the sustainable environment, sustainability, sustainable manufacturing. So everything is sustainable. If you go back to 3 decades or 4 decades back, no one was actually talking about sustainability. People were talking about environment, but they were not talking about sustainable development, sustainable engineering, sustainable manufacturing. But all of you might have heard this word sustainable in the recent time significantly. Everywhere there is either sustainability or sustainable development goal. So we need to understand why are we talking about sustainability and how thermal energy storage materials are linked with the sustainable part. So, and as I said that why do we talk about sustainability? Why do we talk about sustainable environment? That means there is a threat to this sustainable environment we are talking about. So what is the biggest threat? So to understand this threat to the sustainable environment, we need to understand the natural resources available and the reduction of natural resources available. So, for example, 3 4 decades ago, we did have a lot of petroleum products and other natural resources which have been depleted now, and we do not have that much natural resources available. And what is the reason? The reason is very simple. The world population is increasing. uh, like 3 4 decades ago, the world population's requirement of fossil fuels or the natural resources and the availability of natural resources, the between this demand and supply was very narrow. The gap between these two were very narrow. But as the population kept on increasing, the availability of natural resources kept on decreasing. So this gap between requirement of the people by increased population and the availability of fossil fuels and other natural resources, this gap kept on increasing. Now when this gap increases, that means there is a threat to the environment. Now the environment is in danger because the gap is continuously increased and it has widened a lot. We do not have natural resources available. That means we need to have more and more new renewable energy sources to bridge this gap of energy demand and supply. Similarly, we also need to have other sources to support the renewable energy sources, because all renewable energy sources have their own limitations. For example, solar energy is available in the daytime. It is not available in the nighttime and on the rainy days, cloudy days. Similarly, wind energy also has its own limitations, ocean energy and then geothermal energy and tidal energy, hydro energy. All these energies are there, but they have their own limitations. So when they have their own limitations, we need to have something which which supports these availability of renewable energy. So I would say that availability of renewable energy or the utilization of renewable energy and the storage of that available energy when it is available and utilize it when it is not available. If we club both of them, then we get the environment sustainable. So the environment sustainability can only be achieved when we have a combination of renewable energy sources and the energy storage. So when I say energy storage, it can be mechanical, it can be chemical, it can be thermal. A simple example of energy storage is your mobile phone, your own mobile phone, your own laptop. The mobile phone has a battery. You charge in the morning and you use it for throughout the day. How? Because it has an energy storage device. It is a battery. So the battery is an electrical energy storage device. During this lecture, we will be talking about thermal energy storage part. But the energy storage is energy storage. We must be able to understand that. So as I said, that sustainable development can happen only when we club renewable energy and the energy storage. In order to achieve this sustainable development in 2015, I think in September 2015, United Nations had given the 17 goals to the world to achieve by 2030. The government, the world governments are bound to achieve these goals by 2030. So I'll not be discussing all these sustainable development goals, but I'll just tell you one thing, that whatever we are doing, whatever research you are doing, you are addressing by default, directly or indirectly, at least one of these sustainable development goals, which are primarily known as SDGs. So you will find these SDGs everywhere these days. So remember that whatever you are contributing, whatever research you are doing, you are actually contributing towards sustainable development goal, directly or indirectly. So before understanding the thermal energy storage part, we must understand very basic idea of thermodynamics. So I'll not take much time on that. We know that thermodynamics is nothing but a science of exchange of energy. When we talk of exchange of energy between two systems or between system and surrounding, we need to understand what are the different types of systems available. So there are three types of systems that we generally analyze in thermodynamics. One is known as closed system, one is open system, and one is isolated system. So the closed system is something in which the energy gets transferred between the system and surrounding, but the mass doesn't allow. For example, I have a cup of tea with me at the moment, which you can see. After some time, the energy will transfer out of it. This tea will get cold, but the amount of milk will remain same for quite some time. So that means it is a kind of closed system. Open system is something which allows both energy and mass transfer, and the isolated system is something which doesn't allow anything to get transferred. That is your thermos in which you keep hot water or hot milk for a longer period of time. Although it has some conductivity, the energy gets transferred after some time, but you can still keep it for a longer period of time. So in continuation to this, what is thermal energy? When the thermal energy or when the energy is transferring between system and surrounding or between two systems, this calculation of energy is very simple. You can calculate using this expression: E is equal to mc delta T, where delta T is the temperature difference between these two objects, m is the mass, and C is the specific heat. So this is a simple calculation I wanted to bring to your notice. And then this thermal energy or energy can be transferred into two ways. either in the form of sensible heat or in the form of latent heat. Sensible heat is something that we can sense. For example, we are increasing the temperature of water. We can sense the hotness or coldness of the water. That is called the sensible heating system. Sensible heating or cooling. But when there is no cooling or heating, there is only phase change. That means there is some hidden heat requirement to change the phase of the system. That hidden heat is generally known as the latent heat. So somewhere it is written here, latent heat. For example, the melting of ice or the solidification or the freezing of water capped into the refrigerator, the freezer of the refrigerator. So we keep the water in the tray. After some time, the water converts into ice. So the conversion of liquid to solid or solid to liquid, wherever there is a phase change, or maybe liquid to vapor or vapor to liquid, wherever there is a phase change phenomena occurs, there is a requirement of latent heat. So the heat can be transferred either as a sensible heat or latent heat. So there are materials which are able to absorb or store sensible heat. There are materials which are capable of storing latent heat. For example, a rock, a simple rock or piece of stone. A piece of stone, if you keep it under the sunlight, direct sunlight, after some time it gets hot. You might have experienced, not might have, you have definitely experienced that in your life, that when you keep a small stone outside your home on the rooftop, in the summertime, after some time it gets warm, hot actually, very hot. That means it has stored some amount of sensible heat. Latent heat you have seen in your life many times by converting ice into water or water into ice. So we'll take this concept of sensible heating and latent heat, and I'll tell you how this thermal energy storage comes into picture. How do we get the idea of thermal energy storage? Once you know what is thermal energy storage, then you can understand about the materials for thermal energy storage. So I'll spend 2 minutes with this and then I'll go towards the thermal energy storage materials. So this classical example I have taken from the thermodynamics book written by P.K. Nag. The example is my problem or my intention is to convert minus 15 degrees centigrade ice into 150 degrees centigrade of vapor. When you want to do that, there are some phases, some stages involved into it. These stages are, you have to convert minus 15 degrees centigrade ice into 0 degree centigrade ice. Then this ice will be converted into water at the same temperature. Then this water will be converted into 100 degrees centigrade. Then 100 degrees centigrade will be converted into 100 degrees centigrade vapor. And then 100 degrees centigrade vapor will be converted into 150 degrees centigrade of vapor. So what are the different types of heating or heats or energies involved in this entire process? We'll see one by one. From minus 15 to 0, it's a sensible heating system because we can sense the hotness and coldness of this. So sensible heat will be required. But for converting ice into water at constant temperature, we will require latent heat. Then from 0 degree centigrade water to 0 degrees 100 degree centigrade water, again sensible heat, then latent heat, again sensible heat. So you can have a look at it for a moment and then you will understand where the sensible heat is required, where the latent heat is required. Now, if you do a simple calculation, the 0 degree centigrade ice, the conversion of 0 degree centigrade ice into 0 degree centigrade water will require 333 kilojoule per kg amount of heat. Right? If you do a very simple calculation, let's say from 0 degree centigrade water to 100 degree centigrade water, you can use mc dt, mc delta t, and you can calculate the value of amount of heat required. Now, I have done a calculation for converting water from 1 degree centigrade to 80 degree centigrade. And the amount of heat required is 332 kilojoule per kg. So what you can see here, this latent heat is equal to this sensible heat. That means if by any means I can store, if I could store this much of energy, later on, this energy can be utilized for heating the water from 0 degree centigrade to 80 degree centigrade. And since it is a winter time, you people have observed that we all need hot water for almost every uh, purpose at the home, for cleaning, for bathing, for utensil cleaning, for clothes, for washing, for bathing. We need water for everything, hot water for everything. And the temperature that we require for bathing is not more than 45 to 50 degrees centigrade. It's even a lot temperature. For cleaning, we don't require a temperature of 60, 65 degrees centigrade. For washing also, we don't need that much temperature. That means if by any means we could store this energy, we can do all our household jobs by warming or heating up the water later on. So this actually triggers in the scientist mind. This triggered in the scientist mind then that why we can't store this energy, because this much energy is required to heat up the water from 0 to 80 degrees centigrade. So let's store it. It might be a vague idea when it came into their mind, but now it is not at all a vague mind idea. People are actually doing it. We all are doing it. So here the idea of energy storage comes into picture, and then there are three type of energy storage can happen: sensible energy storage, latent energy storage, and the chemical energy storage. Sensible energy storage by elevating the temperature, latent heat storage by changing the phase, chemical heat storage by exo and endothermic reactions. So for example, wherever there is a reaction happening, chemical reaction happening, some heat is emitted out of this reaction, that's called chemical heat storage. So why do we need to store energy? Here we could understand that there is a possibility to store, there is a possibility to utilize this stored energy, but why do we require, why do we need to store the energy? So this you can understand with this example. Uh, just think about it, that how much temperature your body require in general. In the summer, when temperature goes beyond 35 degree, we start feeling hot. In the winter, when temperature dips below 20 degrees centigrade, we start feeling cold. That means there is a temperature range in which we all feel comfortable. Generally, this temperature range is between 22 to 26 or 27 degrees centigrade. If the temperature drops below 22, we feel hot, we feel cold. If the temperature goes beyond 27, 28, we start feeling hot or warm. So that means there is a temperature range. So this temperature range I have kept by in the green line is the desired temperature of the body. But what actually happens? Do we get this desired temperature for throughout the years? No, we don't get. Especially now. Now imagine a month of November. What happens in the month of November? In the month of November, days are very hot, the nights are cold. So it so happens that in the daytime, we are using air conditioner and fan sometime, but in the morning time we are using geyser. We are using hot water for bathing. So we are using hot water for bathing, but in the daytime, for body comfort, we use air conditioner because the temperature is very high. Because the night temperature is around 20 degrees centigrade, the day temperature is around still 35 degrees centigrade. So there is a huge temperature variation. So this temperature variation you can follow with this red line. Now the temperature increases in the daytime and temperature decreases in the night time. So in the daytime we have heat surplus which we don't require at all, but in the night time there is a heat deficit because in the morning time we feel cold, in the night time also we feel cold. So there is a heat deficit. Now what to do? Can we store this heat surplus available in the daytime and utilize in the night time? There the concept of thermal energy storage comes into picture, and that's how the thermal energy storage is important. So it is the similar thing that why do we need thermal energy storage? We need to match supply, the energy supply and demand. We need to do the peak energy saving, the flexibility of the system. We can use the system many times, but there are some parameters which we need to look into when we are installing the thermal energy storage. We need to check its quality, the capacity of energy storage provide, the energy density, and the power it can give us. So this we have already discussed how the sensible heat is denoted on the curve, and then how the latent heat and thermochemical heat. So it's a repetition of these things. All right, the same. Now, as I was mentioning that there is, when we heat up something, it requires some sensible heating, then latent heating, and then sensible heating. So there is a portion wherein the phase changes, right? Phase changes. So there are materials which are able to store the energy while changing their phase. For example, ice. When we heat up the ice, it melts and it changes its phase from solid to liquid by absorbing some amount of heat. So when the water is a material, it is able to store some energy. We call it energy storage materials, thermal energy storage materials, or the materials for thermal energy storage. In generic term, they are known as phase change materials. They are known as phase change materials. So the materials which change the phase and store the energy, also change the phase and release the energy. So they have the capacity to store and release a large amount of energy when they change their phases. So look at this diagram. This blue hemisphere shows that, or you can say the blue circle, blue bowl, whatever you want to call it. The blue color shows the liquid, and the yellow shows uh, the solid. So the liquid is being converted into, the solid is being converted into liquid. So blue denotes solid, the yellow denotes liquid. So the solid is being converted into liquid. The second phase, the liquid is being converted into solid. So when the solid converts into liquid, it stores the energy. When the liquid releases its energy, it becomes solid. The same thing happens in the case of water and ice phase change. The water releases its energy and converts into ice. The ice stores the energy and converts into liquid. So energy storage and energy release, it does the both. So we call it phase change materials. Similar to ice, there are n number of phase change materials. We'll see some of them, and what all analysis we do on these phase change materials or PCMs. We'll see them one by one. There is a big classification of these PCMs. So as you can see, PCMs are classified as solid liquid, liquid gas, solid solid. Solid liquids are the most popular PCMs, classified as organic, eutectic, and inorganic. Organics are paraffin, fatty acids, alcohols, esters, and others. Inorganics are generally salt hydrates. Solids are polyurethane, polybutadiene, and others. We generally don't deal with solid. We deal with organic and inorganic. So organic has their own properties, inorganic has their own properties. These red color texts are the properties which these individual materials have. So the organic materials show the simultaneous melting or effective solidification. They have high heat of fusion or latent heat, but they do have a very low thermal conductivity. For example, paraffin wax, it has a very good latent heat of the order of 150 joule per gram or 200 joule per gram, but the conductivity is of the order of 0.15 or zero point 0.2 watt per meter Kelvin. So, since the conductivity is very low, there is a requirement to enhance their conductivity. Okay. Now, how do we actually use the PCM in the actual application? So please have a look at this. I'll quickly go through this. Uh, you just imagine this is a building wall, and the building has been designed in such a way that there are two portions of the wall. Between two portions, there is a layer of PCM. Now, I have drawn this diagram for four different phases of the day. Let's start with the early morning. Early morning, maybe 5 o'clock, 6 o'clock, or 7 o'clock. When the outside temperature is 26 degrees centigrade and the inside temperature is 23 degrees centigrade. Inside means inside the room temperature. So here is the room you can imagine. Now what happens as the day progresses, we reach the midday around 12 p.m. or 1 p.m. The outside temperature increases from 26 to 35. But as the temperature increases, the heat starts transmitting through the wall. So what you can see is the PCM was of gray color. Now the PCM is of red color. So this gray color shows the solid portion. The red shows the liquid portion. The PCM is able to absorb this entire energy and then starts getting melted. So when the PCM absorb energy, that means they are not allowing or they are preventing this heat to get inside the room. They are able to absorb the heat. So when the heat doesn't go inside the room, the inside temperature still remains same. As you can see, 23, 23. But the outside temperature increases. That means in the morning time we feel comfortable. In the noon or afternoon time we feel comfortable. Let's go towards the evening time and see what happens. In the evening time, when the outside temperature dips a bit from 35 to 30, the PCM has already saturated by now. So the PCM has a capacity to store the energy. After that, it will start the transmission of energy. So it will transmit the heat towards inside the room from high temperature to low temperature. So there will be a slight increase in the room temperature from 23 to 25. That means humans, we will still feel comfortable in that temperature. In the night time, maybe 12 midnight, 1 a.m., 2 a.m., 3 a.m., the outside temperature is pretty low. Then the PCM will start releasing heat towards outside because we all know that the heat transfers from high temperature to low temperature. Inside is the high temperature, outside is the low temperature, so the heat will transfer in this direction. The PCM will release its heat and will convert into the solid phase again. So we started from solid phase, liquid phase, then the solid phase, and then again the cycle will start like this. So the cycle will go from fourth to one, one to two to three, four. So one, two, three, four, one, two, three, four. This will be the cycle of PCM. So the PCM will melt once in a day, will solidify once in a day, and that's how PCM works. So there are different types of organic and inorganic PCMs. So PCMs can be utilized as either single or mono PCMs, or we can also prepare the eutectics of them. So you can quickly see that there are some organic materials, some properties have been shown here. Their melting temperature, their latent heat of fusion, F stands for fusion, their specific heat, their conductivity. You can see the conductivity is very low. The water is an inorganic material, the conductivity is 0.6. Tetradecan is an organic material, the conductivity is 0.15. So the conductivity of all organic materials are very low. Paraffin 0.2, naphthalene very low again, caprylic acid very low again, and all of these are organic materials. You can see their conductivity is very low. Then the PCMs can also be prepared as an eutectic. We can mix two or three PCMs and come up with one single materials. So we do that in order to tailor their melting point. For example, this we can understand as that I have two materials which are available in two different melting temperature. One is at 40 degrees centigrade, another is at 45 degrees centigrade. But my application requires a a material which should have melting temperature of 42 degrees centigrade or maybe 42.5 degrees centigrade. Very peculiar temperature, but I don't have a material available. So what we will do, we'll mix two materials. One is of 40 degrees centigrade, one is of 45 degrees centigrade. We will mix them in a different ratio until we find a material with a melting point of 42.5. So that's how we prepare the eutectic. It can be binary, it can be ternary, or it can be more. So depending on the materials availability and the requirement. Okay. When we are utilizing the PCM, it must have certain properties. It should have high latent heat, it should have high specific heat, it should have high thermal conductivity, it should have high chemical and thermal durability. As you can see, longer chemical stability, and it should be non-toxic, it should be easily available, it should be inexpensive. So these kind of favorable properties it should have. Okay. Now, generally what we do with PCM, let me take the time, please. All right, we still have time. So, This shows the entire research domain that we work in using different kinds of PCMs. So there are three categories, three segments under which we work. We do thermal cycle testing of PCM. Thermal cycle testing is basically done to check their uh, thermal durability and the chemical durability. So as we were discussing previously, that a material, a PCM, will melt once in a day and will freeze once in a day. So how long we can use these materials? Obviously, when it changes its phase again and again, after some time, its properties will get deteriorated. So how much depreciation it will experience, that is important. So after a year, 2 years, or 5 years of uses, what will be the latent heat? What will be the melting point, and what will be the conductivity this material will have? So this kind of melting and freezing treatment is done using a thermal cycle testing. For that, we have developed an in-house tester in my current university. The second part that we work on, as I was saying, that organic materials have very low thermal conductivity. So there is some uh, treatment required for enhancing the thermal conductivity. So for that, this is one of the example I have quoted here. Nano enhanced PCM means we mixed nanomaterials with the organic PCMs for enhancing the thermal properties. So I'll show you one by one and how do we do that. And then the form stabilization. Generally, why do we do this? If we are using PCM, it will melt and freeze. Once it is in the molten state, we will require a container to contain it. Just imagine paraffin wax that we utilize to make the candle. When the candle melts, it just flows on the floor. So we require a container for that. When we are using it in the actual application, a container has to be required to contain the molten PCM. Similarly, for the nano enhanced PCM means after mixing the nanoparticles or any other materials, once it is in the molten state, it will flow away. To contain it, we require a container. In the case of now, when we require a container or when we use a container, the container material might be reactive with PCM. Generally, with organic materials, they don't react, but with inorganic, they will react. But the container will have its own weight, and the container is not adding anything into thermal properties. It is simply increasing the weight of entire thermal energy storage system. So we don't require that. We don't want thermal energy storage system to be bulky. So that's an additional burden on us. To, to, to get rid of that, we prepare form stable materials, or we also known as shape stabilized materials. So that means we develop a kind of composite materials wherein when the PCM gets melt or when it is in the molten state, it doesn't flow away. It retains its shape even in the molten state. So I'll tell you how do we do that. So these are the three fronts that we rigorously work on. This was the tester that we had developed, and we still use it. We can use it for infinite time, where this machine doesn't stop and it doesn't require any human intervention. Once you turn this on, it will work on its own for thousand number of cycle, for 10,000 number of cycle. The maximum it can be used for 99,999 number of cycles. So after that, it will be 1 lakh. That means 6-digit value. So this machine has been set up to 5-digit only. So I can, one shot, I can use it for 99,999 times of melt and freeze for a single PCM. So as you can see it, we can set a minimum and maximum temperature here. And here the number of cycle is shown. You can see that the 100 was the number of cycles which was set earlier. Currently it is at the 92, which means that material has already been melted and solidified for 92 times. Here you can see that the maximum temperature was 80 and the minimum temperature was somewhere around 35. So what happens when the material is at 35 degrees centigrade, the machine will be turned on and the temperature will increase up to 80 degrees centigrade. Once it reaches at 80 degrees centigrade, the machine will automatically cut off the heater and the power will be transferred to the cooling side. So the cooler will start. When the cooler starts, the temperature starts decreasing from 80 to 30, and this happens automatically without any human intervention. And then there are some heaters, there are some slots for PCM. So it's a simple machine setup that we have developed here. For enhancing the conductivity, we need to add up some foreign particles into the PCM. So adding the nanoparticle is one of those way. So what happens here? We melt the PCM and the nanoparticles are added into molten PCM. That's how the nano enhanced PCM gets developed. So what you can see is the white spots are nothing but the nanoparticle. But the one thing to be noticed here, that when we are adding nanoparticle, the dispersion of nanoparticle should be uniform. Otherwise, nanoparticles have a property to get sediment and to agglomerate. They'll come towards each other and they will agglomerate and will become like a cluster. That shouldn't happen. So to break the cluster, there is a way we use that. There's a way to do that. We add some more material so that the cluster doesn't happen and the agglomeration doesn't happen. So that has to be avoided. And then the form stabilization, what we do, we take a porous matrix, or we can say we take a porous material. Into this porous materials, or into the pores of these materials, we add PCM. We add PCM by the rigorous mixing process. Once this PCM gets settled into the pores of these porous materials, after getting melted, this PCM remains into the pores. What you can see on the right hand side, this we call FS-PCM, form a stable phase change material. So when the material gets melted, the PCM is retained into the pores. It doesn't flow away, it doesn't come out of this material. So because of that, it is known as shape stabilized, because it keeps its shape retained, or we also known as form stabilized. It keeps its form very much stabilized. So we have tested a number of PCMs for that. Uh, I'll straightway go to that. So we have tested various paraffin wax, palmitic acid, myristic acid, polyethylene glycol of different molecular weight. I have just added here one, but we have tested like 7 8 types of different molecular weight of polyethylene glycol. We have also tested the esters that I'll show you. So yeah, I'll show you some of the results for you to have an understanding of this PCM. What we do here, it is the schematic of the same experimental setup that you had just seen. So what we did, we kept the PCM into these 6 slots. Then there are 3 heaters to heat up these materials, and then there are 4 coolers attached on a heat sink to cool the materials after heating is over. So the temperature was between 30 to 100 degrees centigrade. As I was mentioning, it will go from 30 to 100, 100 to 30 on its own. So without any human intervention. So we did it for 1500 melting and freezing cycles non-stop. So it took around you can say it took around maybe 2.5 months to complete this entire 1500 cycle. And then we tested using different machineries to effect of these thermal cycling on the thermal properties. So what thermal properties we do analyze? So as I said, one was latent heat and the conductivity and the chemical stability of these materials, whether the materials was chemically stable or not after 1500 cycles. What happened to its chemical bondings, the functional bondings of these materials. So we'll see that one by one. For example, paraffin wax. What you can see on the screen is these are the DSC curves. DSC stands for differential scanning calorimeter curves. So this is a machine which tells us the amount of latent heat a material has and the melting point of the material. So the melting point of the material we can see at this point, because this is the point where the melting starts, and then the melting continues and ends here. So this we call onset point. This is the end set point. Now the area under this curve is the total latent heat a material can have, because this is the point where melting starts. This is the point where melting ends. So between this, there is a curve. If we calculate the area under this curve, this gives us the latent heat of this material. So I have overlaid these curves between 0 to 1500 cycle. So this zeroth cycle means the material, the fresh material that we had received from the vendor. Then after 100 cycle, after 500 cycle, after 1000 cycle, and after 1500 cycle. And then what was the results? The melting temperature changed by minus 2.57 degrees centigrade after 1500 cycle. The latent heat of fusion, which is the melting, also reduced by 14% after 1500 cycle. That means, uh, let's say the latent heat was 100 when we bought this material, and then after 1500 times of melt freeze, the latent heat reduced to 86 joule per gram. That means a 14% reduction. So how do we see that? One cycle in a day, one melt and one freeze cycle in a day. If we have 365 days in a year, if I exclude the rainy days, cloudy days, then I roughly get 300 days in a year. So one cycle in a day, 300 cycle in a year, and then 300 multiplied by 5. So 5 years. After 5 years, this material will lose its 14% of latent heat, roughly. Because this is the laboratory test. In actual experiment, this might be a little different. But roughly, we can say that 14% of its latent heat will go waste, will reduce. But 86% is still there. That means the material can be very well utilized or used for continuous or consecutive 5 years. Similarly, uh, we we did these studies, the thermal cycle studies for palmitic acid, which is another organic material. As you can see that at zeroth cycle, its latent heat was 213 joule per gram. After 1500 cycle, it was 175. Similarly, for myristic acid, from 202 to 220. In between also you can see. This was for polyethylene glycol 6000 molecular weight, 231 to 173. I have tabulated these values. Okay. So now this gives you a comprehensive understanding of how thermal properties changed over the period of time. As you can see that melting temperature of paraffin was changed from 52.9 to 50.33, for PG from 59.9 to 56.11, and so on you can see. Right. The variation in latent heat in the case of paraffin from 133 to 114, that means 14% reduction. In the case of palmitic acid, it was 17.88%, roughly 18%. In the myristic acid, only 0.64%, but in the case of polyethylene glycol, it is roughly 25%. Now, as an application engineer, what do you want? You want your material to lose minimum amount of latent heat after certain number of cycle. And that's what is happening into myristic acid. After 1500 number of melt freeze, it loses just 0.64% of its latent heat. So as an application engineer, you can say your customer that myristic acid is the best material out of these four because it doesn't lose its latent heat capacity over the period of 5 years. And the polyethylene glycol is the worst material because it has lost its 25% of total latent heat capacity. But being an honest and an intelligent real application engineer, you have to see the trend, all this trend. So I want all of you to have a look at this trend. What is happening after 100 cycle? Is the value reducing or increasing, decreasing or increasing, decreasing or increasing? You see, after 100 cycle, in the case of paraffin, it decreased, but after 500 increased. After 1000 decreased, 1500 decreased. In the case of palmitic, decreased, increased, decreased, decreased. In the case of myristic acid, decreased, decreased, increased all of a sudden, and then increased. PEG decreased, 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 decreased. So PEG has shown a very beautiful pattern. That means being a real application engineer, I can tell my customer that I am giving you a guarantee that polyethylene glycol will lose its definitely 25% after 5 years. But I cannot guarantee on myristic acid, palmitic acid, and paraffin because their behavior is like sine wave, increases, decreases, increases, decreases. I cannot comment on its applicability and the durability. So your customer will understand that PEG has a trustworthy values. I can trust on PGs. Now it's up to me whether I want to use for a year or 2 years or 5 years or 10 years. But I know that after 5 years, it will lose its 25%. Still, if I can manage with 75%, I'll go with it. But I cannot trust on myristic acid, palmitic acid, and paraffin. So that way, a real application engineer has to see the pattern of these values. And then these are FTIR curves, Fourier transform and infrared spectroscopy. So these curves basically tell us about the functional bonding of these materials. You can spend few moments with it and see what is happening after 1500 cycles of each. I'll not go into the more details of it because this is a deep chemistry which might bother you. So just have a look at the peak and you can see that shape of peaks after 1500 cycles are almost similar to what it had at 0th cycle. That means, that simply means that there are no changes in the functional behavior of these materials after 1500 number of cycle. The material, chemically, the material is very, very stable. Thermal stability we see here, chemical stability we see here, right? And then we also did thermal cycling of fatty alcohol, cetyl alcohol, lauryl alcohol, stearyl alcohol using the same setup for 3000 number of cycles. And you can see that even after 3000 cycle, the variation in latent heat and melting temperature is almost negligible. So these are very, very good materials. Okay, now coming to the properties enhancement of organic PCMs. Organic materials are very, very low thermal conductivity. There are ways to enhance its thermal conductivity. We can add nanoparticles. We can develop form stable PCM. We can do some surface modifications. We can develop eutectic PCMs. We can also encapsulate them into a container or small capsules. So these some of these things can be done for thermal performance enhancement of different PCM. But we need to understand why do we need to do that? Why do we need to enhance the thermal properties or conductivity of a PCM? To understand that, uh, let me tell you one very basic thing. If like these days the temperature is pretty cold everywhere, I mean especially in the North India and eastern part of India and the central part of India. So uh, if you are feeling very cold, you get home, you are feeling very cold, you wear all those clothes, still you are feeling very cold. In that time, what do you want? You want a good heater to warm your body immediately, as early as possible, maybe within 5 minutes, 10 minutes, or 15 minutes. You cannot wait for an hour or 2 hours or 3 hours to get your body warm. Because if you have to wait for 2 hours to get your body warm, then the purpose of heating gets diluted. So I want the heat to be transferred from the heating object to my body at a very, very rapid speed, very, very rapid pace. So this rapid heat transfer depends on one value that we call as thermal conductivity. If you guys are physicist or mechanical or chemical engineer or civil engineer, you might have had a course of heat transfer or thermodynamics wherein you had seen the heat conduction, heat convection, and heat radiation. So there is an equation of heat conduction. Q is equal to minus Ka dt by dx, where Q is directly proportional to conductivity K. If the conductivity is very high, the heat transfers very rapidly. This can also be understood in a very, very layman language. If you have a metal bar, the one part of it, one side of it, you put it to the fire, the other part will get warm, hot very, very soon. But the same time, if you have an asbestos sheet or rubber material or wooden piece, the one side of it is under fire, the other part doesn't feel hot at all. So that means its conductivity is very, very low. You don't want that kind of effect on your body when you are feeling cold. You want a metal bar kind of heat transfer. That means we need higher thermal conductivity to do that. So how do we understand the thermal conductivity effect on the material? One is that you check the conductivity using a thermal conductivity testing apparatus. The another way to do it, uh, what we do is we plot a time temperature curve or temperature time curve. That means just look at these two curves, the red curve and the blue curve. The red line, it goes up and then it comes down. So it makes a mountain. That means let's say it starts with a temperature 35 degrees centigrade. It's a materials line basically, nothing but a material line. Simple PCM. A PCM start getting heat up till this point, and then so let's say this is a charging time, means melting period, and then this is the solidifying period. So one complete melting and then one complete freezing is taking approximately 70 minutes, from 0 to 70 minutes in the case of PCM. Follow the black line. So a pure PCM, pure organic PCM is roughly taking 70 minutes for one cycle for heating and cooling. Now, if I add some nanoparticle into these materials, I know its conductivity should increase. If its conductivity increases, the entire melting and freezing time should be lesser than the pure PCM time. That's what happens here. If you follow the red line, the entire melting and freezing cycle takes roughly 55 minutes. So there is a reduction of 15 minutes after addition of nanomaterials, or by developing a form stable PCM from 70 to 55 minutes. So that there is a reduction in the time, and that's what we want. That is the effect of high thermal conductivity. So thermal conductivity can be increased by inserting the metal matrix, fin tubes, nanoparticle dispersions, etc., etc. There are many ways to do that. So we did many experiments for thermal conductivity enhancement. I'll explain one of them here quickly. We added, we took palmitic acid as a PCM. Solid PM means palmitic acid. This palmitic acid was capped on a hot plate. It was melted. Then the nanoparticles was added using a sonication process, and then it was solidified. So what happens once we add the nanoparticles? If you look at these FESCM images, these are the this is the image of nanoparticles, and these two are the images of PCM with nanoparticles at different magnifications. You can see these white spots are the nanoparticles which have been dispersed uniformly into the materials. Now, thermal properties measurement. Thermal properties measurement means we developed four different kinds of nano enhanced materials. So four different kinds of materials means we did 1% addition, 2% addition, 3% addition, and 5% nanoparticle addition. When we do that, let's say what happens. The latent heat of pure palmitic acid was 213.46. Once we add these nanoparticles, the latent heat decreases. If we keep on increasing the percentage of nanoparticle, the value of latent heat keeps on decreasing. So very easy to understand this, because the specific heat of PCM was high, the specific heat of nanoparticle was low. When you mix these two materials, the net specific heat will come down. This nanoparticles will bring the specific heat of PCM down. So that means the latent heat of the effective composite will be lesser as compared to the pure PCM. And as we keep on increasing the amount of nanoparticle, the latent heat will keep on decreasing. These values were obtained from the differential scanning calorimeter thermogram. Now, what happens is the chemical stability. Fine. So, how the thermal conductivity enhanced? As you can see that we added different percentage of nanoparticles. So there was an enhancement in the thermal conductivity. After addition of 5% of titanium dioxide or titanium nanoparticle, the conductivity of palmitic acid was enhanced by almost 80%. Earlier, it was somewhere around 0.219 or maybe 0.19. And after addition of 5%, it became 0.35. That means if we keep on adding nanoparticle, the conductivity will keep on increasing. but there has to be a bar on the amount of nanoparticle addition. We cannot add more than 5% as the problem of agglomeration or sedimentation of the nanoparticles will increase. So the addition of even 3% is a lot. So generally 3% to 5% is the maximum amount of nanoparticle addition. We shouldn't add more than that. Okay. Then this is nothing but the thermal stability of nanoparticle, nano-enhanced PCM. When we add nanoparticle into the PCM, the thermal stability of PCM increases. Okay. And then the thermal cycling test was also done for this material for 1500 cycle, and the material was pretty stable. Even after 1500 number of cycles, only the 2% of latent heat was decreased. Then similar studies, many similar studies have been done by our research group and other research groups. Many people have added different kinds of nanoparticles into different PCMs and have seen the percentage enhancement of thermal conductivity. As you can see, someone has found 35%, somebody has found 62%, and so on. So this is just a list. I'll not read all these things. Okay, so the last part of this, I'll take maybe 5 to 10 minutes more because it's already more than 1 hour. So the last part of my research domain is development of form stable PCM. So we do develop different types of form stable materials by mixing porous materials into the by adding phase change materials into the porous materials. And this is the concept that we had already discussed earlier, that the PCMs are added into the pores of these materials, and then after some time it becomes something like this. So the PCM gets entrapped into the pores of these materials, and we call it form stable PCMs. So we have done a lot of amount of work on development of form stable PCMs. I cannot explain each one of them, but if anybody is interested, I have shown my email ID in the last slide. You can capture that and then you can ask me anytime. You can send me an email for that. So I'll take some examples. What we did, we bought urea from the market. Everybody knows what urea is. Urea is added into the soil for making it more fertile, so that the better production of crops can be done. So we bought from the urea. Also, the urea is an industrial waste. So we bought the waste material from market. Urea is very cheap, and then we did the pyrolysis of urea using an oven, simple oven. So we burned this urea at 550 degrees centigrade for almost 2 to 3 hours, 2 to 2.5 hours. And then what happened? The urea was of white color. After burning it for like 2.5 hours, we got this kind of materials. So after doing the chemical testing on that, we realized that this is graphitic carbon nitride, and this carbon is not black; it's a white carbon, uh, like kind of uh, ivory color of carbon. So we generally call it white carbon. It's not a black one. And the chemical name for this is graphitic carbon nitride. So what we did, we burned the urea at 500 degrees centigrade, and then it was converted into graphitic carbon nitride. It's a chemical representation of that, GC3N4. And then this is the FACM image of graphitic carbon nitride. You can easily see the pores here. If you can look at it critically, you will find the holes in this material. These holes are nothing but the pores in which the PCM will be impregnated. So these are this kind of hole. The PCM will be impregnated into this. So there is a process to do that. This was the process that we had followed. We call it a vacuum impregnation method. So in this vacuum impregnation method, vacuum is created into the beaker, and then the GCM, the graphitic carbon nitride, was added into small parts into the liquid PCM, and then it was rigorously stirred. and like stood for maybe around 1.5 to 2 hours. So after stirring, it was allowed to solidify. It was after solidification, after freezing, what we got is this. This we call FSPCM or FSOPCM, whatever you want to call. FSOPCM means form stable organic phase change materials. And simply we can call it FSPCM, form stable PCM. So it is a mixture of palmitic acid, sorry, one fatty alcohol, and then organic PCM, and then graphitic carbon nitrate. And then the thermal properties was done. Okay, this is the leakage test that we generally carry out to understand whether there is any flow in the molten state or not. So to understand that, you can see that this SaOH is still alcohol. This is still alcohol. GC3N4 is the graphitic carbon nitrate. So what we can see is 65% PCM was added into the graphitic carbon nitrate. Then 70% PCM, I mean the still alcohol was added, and then 75% alcohol, 75% PCM. And then it was capped at a certain temperature. The temperature was the higher than the melting point of the PCM. Now, what you can see on this screen, you can see some impression here around it. That's nothing but the molten PCM. So when the 65% PCM we added, 70% PCM was added, there was no leakage at the same temperature. But when the amount of PCM increased, there was a leakage. So that means we can have this composite as an optimum composite for thermal energy storage purpose. At the same temperature, the PCM was melted, but this composite was not melted. So that means that we call it the form stabilization or the shape stabilization has been achieved because the PCM is not melting at this particular point. Then some thermal characterization was done. This is still alcohol and form stable PCMs. This is a differential scanning thermogram, and its latent heat and other values were found out. Thermal conductivity was a very interesting result. The graphitic carbon nitrate, as you know, that it's a simple carbon material, but it's a white carbon material. It has higher thermal conductivity. Once we added into the PCM, the thermal conductivity was enhanced, was doubled, almost doubled, from 0.22 to 0.49. And when it is doubled, it takes the lesser time to complete one melting and freezing cycle. So you follow this black line for the pure PCM and the red line for composite PCM, for FSPCM. So the composite PCM takes lesser time for one complete melt freeze cycle. And then the thermal cycle was also done for 1000 cycles, and the material was pretty stable thermally and chemically after 1000 number of cycles. And there's another work that we did. The coffee seeds. After preparing the coffee, we just throw the seeds, those seeds. So we collected those seeds, coffee seeds, and then we did the pyrolysis. And we converted that into the biochar, and then we activated the biochar for having the more surface area of those pores. And then one PCM myristic acid was added into it for enhancing the thermal conductivity further. The nanoparticle was also added into it. So it's a complex procedure which is very difficult to explain here, and it will take a lot of time if I keep on explaining it. But yes, this is another work that we had carried out very recently. It's already published, and this particular work gave a very fantastic result. You can see the thermal conductivity was enhanced, almost doubled again, from 0.23 to 0.487, and the thermal properties were also very nice. Uh, the thermal conductivity of pure PCM, the latent heat of pure PCM was 175, and the composite PCM was 98 and 1011 for the different percentage of porous materials. Okay. That was the another work that we had done. We took the date seeds, we converted into biochar. Interesting to know that these date seeds was provided by the organizer of this FDP, Dr. Abhishek Sharma. Thanks to him. So we converted these date sheets into the biochar. We activated them, and we converted into a very good porous materials, and then we found some very good form stable PCMs. So all these works either have been published or in the process of publications. So these materials, you can see that after activation, you can see the pore size have increased a lot. And that's what we want, so that the maximum amount of PCM can be fit into it. Okay, so there is a lot of similar works with the different results, different materials. I'll not explain all of these. And some bio waste materials were also utilized. We also utilize vaccines for thermal conductivity enhancements. So many work have been done. And this is the repetition date sheet biochar. We already seen that. So yeah, and then these thermal energy storage materials have found their applications in almost every kind of industries. The textile industries, in the textile industries, the smart apparels are built, are manufactured. These smart apparels are nothing but the clothes for athletes, because athletes sweat a lot. So when they sweat, they want their material, their clothes to absorb these sweats. So these PCM based clothing are able to do that. Solar water heating, air heating systems have also utilized many PCMs. Building materials and many waste heat recovery systems have also utilized PCM. Food industries have also seen. Automobile industries, the EV cooling system, battery cooling system, photovoltaic electricity. Also, these days the photovoltaic panels are integrated with PCMs for efficiency enhancement, and yes, the battery thermal management system. So as there are many applications. Thank you very much for your patience. Sorry if I have taken a lot of time, but yeah, that's all. People can contact me on this email ID if they are interested in working in these areas, or if they have any queries related to this. So thank you, Dr. Abhishek, and the
Thank you
amazing
very much,
team.
sir. Thank, thank you, sir. From basic to advanced level, and even your practical experiences and practical application of face material you have discussed. Really, I'm very much thankful for enlightening us, sir.
Thank you very much.
Now, may I request the participants if they have any question or they want to ask anything? Yes, sir. Please ask. Sridhar, sir.
Yeah, yeah.
Yes.
Sir, good evening. It's a good
Good
presentation.
evening.
Here my question is, sir, as you know, in thermal power stations, steam is generated. A lot of steam is generated to generate the electricity, but the steam is goes as a waste into the atmosphere through
Yes,
boil.
true.
Yes, sir, no, sir. I'm right.
Yes, yes, you are absolutely right, and it's a
So,
very valid question.
so can't you use that steam by using some conductive materials to some electricity or something else?
Uh, some industries are already doing that. They are calling it waste heat recovery, because the heat is going waste. So they are utilizing this waste heat for melting the PCMs. They have already built up a thermal energy storage system using PCM. So they melt the PCM and keep the energy stored. Later on, these stored energies are being utilized to heat up the water and the air for different purposes in the plant. So they are already doing. I'm not saying that all industries are doing, but some industries have already started doing that.
Okay. And one more question, sir. You have taken that what you call urea taken and used coffee powder you have taken and you pyrolyzed that and impregnated with the PCM. Am I right, sir?
Yes, yes,
Sir, is there you do have any other options? Wood charcoal and coconut charcoal. I think coconut charcoal has very fine surface area and
yes.
yeah.
You
Even,
see, this coconut shell, almond shell, not almond, the walnut shell, coconut shell, and other shells of other things. Even the this thing. the sugarcane waste, all
Yeah.
these things are being pyrolyzed to convert into the char, and the char is being utilized as a porous materials. So people are working on that.
But I think coconut charcoal is best option, but it has a very fine surface area. According to my
Need
knowledge.
to need to check because I have not worked on that. But as you are saying that yes, there is a possibility. I have seen few work on coconut shell.
Yes.
So people have used coconut shell. I don't remember the exact value of their pore sizes, but people have used that.
Okay. Okay. Thank you very much. Good presentation.
Thank
Nice.
you very much. Thank you very
Thank
much, doctor.
Anyone? Any more question? Okay. So I'm closing the session. So thank you, Ravi sir, once again for
Thank
enlightening us
you.
regarding thermal energy storage, patience materials, and really talk was very wonderful. Thank you very much, sir.
Thank you, Dr. Abhishek. Thank you very much. Thanks, everyone.
Yes, sir. So next session will start at 7:45. So we will take a tea break. Then after 20 minutes, we will start the next session. We are closing the meeting right now.